primary was for evaporate lithology. Then the main aspect of the casing setting that is overpressure, because we needed to know where is the overpressure now. I use sonic ion resistivity for it. CA lithology was a source of identification, and my last one was to know whether it's appraiser or exploration. So I used the porosity block, which was about 3 diameter. Thank you.
Now you introduce Kingsley.
Now my colleague Kingsley is going to talk about casing design.
Just one thing. Let's just try to talk louder and maybe. Okay. One of the things that you say, you just say a lot of I and me. You can just say
just remember, and we will carry on because I'm checking the time.
You can just give me that.
I'm keeping the time.
There is a thingy. Time like a.
Come on, I remember to start at 2:05.
There is a stopwatch there.
It's okay, but approximately anyway it will give the exact amount of minutes.
There we go.
After the half of the.
That's why we're practicing.
Okay, let's go.
Carry on.
Okay.
We need to know that.
Hello guys. Actually, I was the one in charge of expecting the casing design, and we had to select the casing setting with respect to the hole geometry and also the kind of or the weight of the wood we're going to use. And as you can see on this slide, I've carefully written out the steps that were considered, and it's quite a direct analysis of all the work that was done. Here you can see the ellipse of plasticity, which was used in measuring the axial stress of the pipes to see if they could withstand the formation pressures. And also we can see another graph here that compares the tension collapse with the tension of the force against the collapse pressure, to see how with increased tension there's a possibility of fracturing or disrupting the pipe. And then on this other table you can see my design specifications of the kind of casing we've used to drill each of the depths, and you can see they've got different tensile strengths, which would also cope with the formation with the pressure as we go down the formation. And here also you can see that the fundamental basis of casing design is that if stresses in the pipe wall exceed the yield strength of the material, a failure condition exists, and that's the basis of this whole design. And we have to look at the mechanical properties like collapse and burst pressures, axial stress, and the forces acting on the pipe as well. Yeah, thank you. So I'll call up my colleague Pavel.
Yeah.
That was good.
Yeah.
I'm going to continue Kingsley's presentation. My topic was math selection and cementing program. And the idea was in this to start initially relating the maximum amounts of the math required during the entire program. An approach which I used was to calculate the amounts of math in each separate section. You can carry on with these calculations for open hole volume, including the previous one cased hole volume. And that gave me this nice table which identifies the volumes of the mud required in the well in each section, excluding the drill string. And these values show that the maximum amount of the mud required will be 2,132. And during the next step, at the transfer from surface to the intermediate casing, we lose around the 1,000 barrels of the mud. That means we will need
maximum amount of the free storage for the liquid mud, over 1,000 barrels, to dispose the mud and to carry on with our drilling operation into the smaller volumes. After that, I considered the additives which contribute to such properties of the mud like viscosity, density, mud cake, filtration, and other hazards elimination. The main problematic zones in our well were surface and second intermediate section. In the surface casing section, the main problematic zone was because of the presence of H2S influx and of the lost circulation zones, and they were combated by the gunk squeezes and coarse grade materials. Also for the second intermediate casing zone, we had the formation like anhydrite and glacier and shales which are really vulnerable to the hydration, and we use inhibited muds such as additives such as lime or soda ash, which reduce the swelling of the clay minerals. In our well, there are other additives which may be required, but just in case if something goes wrong or we face some particular problems, and such particular problems could be like lack of viscosity, which we improve with adding bentonite and polymers, various clay additives for the filter cake formation, soda ash for calcium or chloride removal when we move from calcium chloride to calcium carbonate muds. It will be necessary, and also Jeep mud might be considered for the anhydrite drilling, but it will depend on the decisions which the mud engineer will make on site. Next part was to make the rough estimations for the hydraulics and solid control equipment. And the main idea in these calculations, you even cannot go into details of these complicated formulas because I'll explain it in a much simpler way. The main idea is that we need to have a positive net rise, and the difference between annular and slip velocity is given by using these formulas. And once we, by iteration, choosing the appropriate flow rate for the annular gap, we have chosen the positive net rise, which means that our particles will be transported upwards. We just use this volumetric flow rate to calculate the pressure drop and just put all these nice values into the table. These tables contains all the necessary numbers to calculate the horsepower. And we see that the maximum horsepower required was during the conductor casing circulation works, and it was around 3,240 horsepower. And that contributed to the final selection of the all hydraulic equipment, and as well contributed to the rig sizing procedure. Next step was in my work to create the cementing program. Cementing program is quite important because it contributes to the integrity and the reliability of the well, and as well isolates problematic zones. In the first step, we cemented 2 casings up to the mud line, that means to the sea bottom. And other wells were cemented only up to a certain reference depth, which is shown on this table. Blends for the muds are shown in the last column of the table, and there as well specified the classes of the cements and certain types of additives, because for the casing conductor casing cementing we were required to have some additives to mitigate the water loss. In the next steps we had for 20 inches casing the additives to avoid lost circulation problems, which was chalcedony. Then for the 16-inch and 13 and 5/8 inches, the main additives were to cope with the thermal gradient, and these additives were simply lignosulfate, which were working as retarders because of the high temperature range in that region. And later we used just much heavier cements because of the poor pressure gradient in the 2 last sections, and these muds were class G, and for the liner, if only required as well. this decision will be based mainly on the assumptions which the cement engineer will make on site, and if we would like to cement the liner, it will be cemented with such class of the cement. There is overall schematic of the well, where we can properly see that conductor is not shown here because it's just 300 feet and the surface casing is cemented up to the mud line. Intermediate first and intermediate second casings are cemented just into the inside of the previous casing for around from 200 to 300 feet to provide the additional structural support, and then we leave such a gap in the production casing in case you will have hot formation fluids going upwards the well, and these temperatures can expand the liquids present in the annular gap, and it will increase the pressure. So we are not willing to have such situation on site, so we simply leave the gap. As well as sometimes we are not allowed to go up to the mud line because the hydrostatic pressure of the cement will put quite big pressures which will exceed the fracture gradient at that area. So we simply cement up to the certain reference depth. Now I'll introduce my colleague Cynthia, which will talk about the other works made during the design process.
Okay, so my part was big program and real estate design and safety and environment. The big program was estimated to be according to the casing sizes that we got. So we started with a conductor surface, two intermediates, the production casing, and the liner. For the first two, we're going to choose mill tooth bit for the size that we choose, and for the next one, we're going to choose PVC bits. Now, according to the methodology that we have, for the intermediate casings and maybe the liner, we're crossing formations about dolomite, limestone, shale, salt, which they might produce somewhere in the bit. Therefore, we might consider to use backup bits for the formations that are risky. Now, we have some recommendations about how drilling the soft formations, which will be maintain a moderate weight and high rotary speeds. And through hard formations, drill best with high weight and moderate rotary speed. This is for a better performance of the bit. Now, the VHA. So this is how our VHA will look like. Now here's the arrangement section. We started with a bit of, this is for the full depth. So we're starting with a bit of 8.5 PVC. Then we had a mud motor, stabilizers, and we have logging tools, stabilizer subs, cross subs for the drill pipe. And we have decided to use drill collars of 6 and 6.25 inches and heavy drill pipe as well to make the transition from the drill pipe of 5 inches to the drill collars. Now, we want to run some tests to know the size of the reservoir. Therefore, these two can be inside of our VHA. We're choosing the measure while drilling tool of directional gamma resistivity and the power and communication. And this is how it would look like. The full view. Now, for safety and emergency environment, it's very important in the companies to have a good teaching of these guidelines. Okay, I will cut that out and say something better. Anyway, so we're going to talk about a few of the safety guidelines and environment, which is waste management. It means when for all the hardest chemicals that we're dealing with. Thank you. We're dealing with in our offshore installations. We're gonna choose to put them in a very. Okay, I'll go back to it. Right, our installations have to be clean, have to be safe, and just make sure of that. Now we're going to do a leakage test to our systems and tanks. It will be an hermetic test. It will be maybe run once a year. Now, internal civil protection program, this is very important since we need, before we take our workers to the installations, we have to provide them with safety knowledge, like where the fire exits are, how to use the extinguisher, how to use the safety equipment in case of incident. It's very important. And of course, when we're in the offshore installations, there must be works like welding and hot works that they're going to be done. So we will need a work permit for all of them. This is very important. And definitely the use of safety acquired equipment while we are in the installation. Now the cost estimates by my colleague, Ferdinand.
The cost estimates were very approximate because we didn't have enough software and enough information and data.
2 million nodes. Unknowns, yeah, because there are many things which we don't know.
Yeah, many things that we didn't know. We didn't know about them, about their cost, and that's why it may be incorrect, but approximately we decided to do the cost estimations based on the projects, design projects that we were dealing with, and basically my colleague Pavel estimated that the surface equipment and flow line and cementing and mud processing were about 400,000, and then my other colleagues gave me the cost estimation about the beats, casing and downfall equipment, then about some other equipment rentals and power and fuel. So basically, we at the end of our design project, we just summarized all our design conclusions, and we made this cost estimation based on that design conclusions. And just to mention that the logic didn't take too much because I only decided to use 5 logic tools due to the fact that it was an appraisal well. So basically, well, the cost for the drilling was about $2,500,000. As far as I can tell, it's not too much.
the thing is, it's left for them to
And this is
spot
just
out what you make, what you're saying wrong.
graphical explanation of the well, and thank you for your attention. Any questions and answers?